I want to thank you guys for joining me on today's webinar Wednesday eDemo. Again, the topic of today is just showing you, doing a run through a flow simulation and showing you the different scenarios, different applications that we can apply this tool for. So just so you guys are aware as well, this will be about an hour-long demonstration here. So what I want to go through today here is, here's kind of just the outline of what we're going to go through. Pretty much going to show you, again, 3 different scenarios where we can apply this flow simulation tool, right? So before I get started, Hawker System sells a suite of different validation tools. Starting with our structural analysis, we have our static and motion simulation, which is included part of our SOLIDWORKS Premium package. So if you have SOLIDWORKS Premium CAD, you'll get the static analysis, motion analysis, where you can run the structural test to see, things are working on your assemblies, your parts, and get results such as stress, strain, and displacement. All right. The next level up here would be SOLIDWORKS Simulation Professional, which gives you a little bit more advanced modules such as a frequency study, a thermal study where your main output is going to be temperature, and then you can run an optimization study where you can do like a design study where you can vary certain parameters and see optimize to minimize the mass, let's say. Right. And the next level up there is the highest level of our structural analysis, which is Simulation Premium, and this gives us now the nonlinear model types. So we now can take a look at that plastic range and a material type. We can get more advanced plots in terms of our harmonic studies, where we can see the response of how things are going to be displacing and stressing at a certain frequency level. So, and then aside from that, we have our CFD software, flow simulation, and this is what's going to be the main topic of today. Right? Within flow simulation as well, it has additional add-ons that you can purchase, which is electronics, cooling, and HVAC, and I'll get back to that in terms of what those are. We also have our sustainability package and our injection molding software as well, which is plastics here. But again, we want to focus on flow simulation here. So stemming a little bit further with that, with flow simulation, what we can do is basic internal, external flow, kind of seeing what's going on within your bodies, within your electronic enclosures, or we can do aerodynamic design, right? Kind of, you have some modeling a car or something that just sees the environment of the air, we can model that fluid really surrounding that body, right? It's also a great tool to do a heat transfer problem, thermal fluid analysis, where with flow simulation we can account for now, again, the fluid of what's going on with this, the heat rising, can have natural convection coming out of these bodies and really get good results in terms of your heat transfer problem there. And then what you see on the right-hand side is our electronics, cooling, and HVAC. These are additional modules that you can get that give you more, in this case, we can get an extended database. So within flow simulation, from the get-go, gives you, a whole bunch of fan curves, a lot of the material database there. But with the extended database, it gives you more information, right? More things that we can do as far as electronics cooling. We can do a 2-resistor type of input, and we'll go over that during one of the scenarios as well. And we can also do an HVAC where you can see we can do comfort parameters, tracer studies. So it's just additional modules where we can get finer or more accuracy level and more information out of our studies there. So going into it here, looking at this photo, how many fluids are actually presented in this, right? And your gut reaction would be, the fluid that's going on in the engine, but what we really have going on is we have air accounting for this here. We have the water in this little like camelback type backpack there, and then we have the oil circulating within the motorcycle as well. And we have exhaust, right? And these are all parameters that we can account for within flow simulation, right? So, fluids are everywhere, and they're very important to us. It's definitely takes it's a lot of information in terms of it's involved within our design process. It's a critical point that we have to account for to be more efficient in our modeling here. So what is flow simulation? Again, it's our CFD equivalent, a computational fluid dynamics tool. So we can simulate real-life fluid flow and heat transfer problems within the CFD here. It's also, again, reinforcing that we can do, calculate or input all these types of different fluids, whether it be an actual liquid fluid or a gas. We can account for, a heat transfer problem here. So definitely being able to assist us in our design process here. And let's see here, and just, again, this is just the tip of the iceberg of what we can do, right? And with these 3 scenarios, these are just going to be the, again, the tip of the iceberg of what we can do with this flow simulation tool, where we can take a look at all the different industries that you guys might be involved with, where we can accomplish with the flow simulation software there. So we can account for, the great thing about this is that since it is fully integrated with SOLIDWORKS, we can vary, different design alternatives where we can change some aspects of the model and rerun our studies there and get our results, right? So kind of the old school way of engineering is, you have your mechanical engineer, you have your designer, and then you have a CFD specialist, right? So you have your model, you chuck it over the fence, and you have somebody who specializes in CFD who has done extensive training within using this tool. But with SOLIDWORKS Flow Simulation, what we really try to do is break that wall, right? And we want to give the power not only to the CFD specialist, but to the mechanical engineer as well, right? To be able to model up, design your model, and then, use this tool to assist you to make better decisions within your model, right? So we can eliminate that time factor where we have to chuck it over the fence and then kind of wait, who knows how long for the CFD analysis to get to your project, right? So we're kind of breaking that wall and empowering the mechanical engineer or the designer with this design process here. So this is just to give you an idea of who uses flow simulation, right? It can really span to any industry. You're not limited, or the tool is not limited to a specific industry. It really, if you care about flow, surrounding flow, or flow going into your system, or fluid heat transfer problem, then this is your tool, right? And you can kind of see all the industries that are involved with that. Right. So, you may be asking, well, why specifically SOLIDWORKS Flow Simulation? Why would I want to go with this software other than, versus another CFD package? Well, if you guys are SOLIDWORKS users, which I think most of you, if not all of you, are, you're already ahead of the curve. You're utilizing the software, you're using it for your CAD, so a lot of the terminology is going to be the same, the interface is going to be the same, the icons are going to be the same, so it's going to have this familiar feel within this tool to really go from a CAD mode to now a flow simulation mode, right? And then kind of adding on to that is that, that's what's really great about it, is that flow simulation is fully integrated within SOLIDWORKS. So you can do those first faster turnaround times, right? Those what-if conditions. What if I change the material of this body? What if I extended this pipe in this direction versus the other, right? We don't have to make those changes, save it out to a generic file format, chuck it over to another analysis tool, and then, wait for things to come back to you and say they're not working, right? You can pretty much just do this all in one shot, run your study, change your model, run it again, and get a faster turnaround time. Right? And then, of course, being that this is something that we sell, it's a single, you will have a single source solution partner, right? This is what Hawker System is all about. Not only are we going to sell or, give you the SOLIDWORKS CAD, but, we'll be able to help you with flow simulation, whether it be consulting services, training, any resource in regards to that, we'll be here for you. All right. So, just to kind of add to that as well is, not only that, if you have a problem with your CAD software, you don't have to go through a lot of hoops. You don't have to go to another, another support system to go to your flow simulation or your simulation studies. It's all just constrained with, or, within that body of Hawker Systems, right? So you don't have to jump through 8 different people to get one answer, right? So now kind of going back into flow simulation here, one of the things that is really great about that tool is that, taking a look at this example of, some kind of electronics cooling enclosure, we don't have to model the air, right? SOLIDWORKS Flow Simulation is going to account for that. As long as it's a fully enclosed environment, it's going to recognize that there's a fluid within that, and we don't have to model that. It'll do that for us, right? It'll recognize all the empty spaces that are within that body as well. And the post-processing of SOLIDWORKS is going to be very easy as well. We're utilizing, again, the same tools that we have from our CAD software. Whether it be a plane or a sketch, we can interrogate these models with the tools that we're already familiar with inside SOLIDWORKS. Right, so, with this here, a big concern with any FEA software or CFD software for that matter is the meshing, right? I know that with different softwares with CFD, the mesh parameter is a little bit cumbersome, right? It's not too intuitive. With Flow Simulation, the meshing is automatic, right? I've used Flow Simulation for a while now. I've taught it, and the meshing parameters are very easy to use, right? The automatic parameters that is set are, pretty good from the get-go. And then, of course, there's also tools to kind of refine it a little bit more in the areas of interest. But, it's very effortless. You don't have to spend so much time on the mesh depending on the project, but it's very easy to use, right? So it has that automatic mesh refinement, captures those narrow channels, and more importantly, it does those partial cells where you may have a boundary within a solid versus air, right? And it'll automatically account for that and, generate this mesh, this good quality mesh to give you good results. And, with CFD, so with this flow simulation, we don't have to guess whether it's going to reach some kind of laminar flow or turbulent flow. It's going to recognize based on your boundary conditions that you input, it's going to determine and give you that flow whether you do have some kind of laminar or turbulent flow there. And we also have, we're able to work with those compressible fluids and, just everything that you would really need to get to the next step in your design process here. So what I'm going to do here now is I'm going to jump through to SOLIDWORKS now, and I'm going to run through 3 different scenarios, right? And the first scenario that we're going to have here is the electronics cooling. And I'm going to run through kind of the setup, the inputs that you can apply, and the results and how we can interrogate the results, really. But in this case, we have a scenario where we have this electronics enclosure, right? We want to know how hot these things get, right? And we want to account for that heat also by inputting some kind of fan as well. So we'll be importing a fan curve, so I'll show you how we can do that. And we'll utilize that 2-resistor thermal model, which is, again, available within our electronics cooling module. And I'll explain a little bit in terms of what that is. Right? So let me jump through SOLIDWORKS right now. Okay, so loading up my SOLIDWORKS here. And what we want to do, again, what we have is we have all these heat sources, right? We have the circuit board, we have that, it has all these chips that are generating some kind of heat power. And then you also see that we have a fin design or a heat sink design here. And then we have, some spacing here for fans. So this is, I was just showing you the simplified version, but what you may actually have here, if I go to my default configuration, you see that this is probably how you may have modeled it, right? This is the closest thing we have to the real life scenario where we have the, this kind of these vents to, of course, let the heat escape from this body. But with any project that you do, whether it be with CFD or any FEA analysis tool, you want to simplify the geometry. Because with flow simulation, there's a lot of tools within the database to simplify these models in terms of specifying that this space actually has this kind of mesh or these kind of vents here. And that's what I'm going to go through with this, one of the things that I'm going to go through within this scenario as well. So if I jump back to my simplified scenario here, let me just load up there. And just keep in mind that we have those vents, and then now if I simplify, if I turn off the transparency, we now have a solid block, right? Those vents went away, those slips went away, but we can account for those slips now within Flow Simulation. All right, so within SOLIDWORKS here, we're now looking at the Flow Simulation, and that was it, right? And that is the great thing about Flow Simulation, is that it's fully integrated within SOLIDWORKS. All it is just a tab over an add-on that we have to turn on, and we're in this mode now. We can always jump back to the assembly, change the model type, or change the model if we need to, open up the parts, adjust it, and rerun the analysis. So just to give you a brief overview as far as how you would set up this problem, within Flow Simulation, we have this wizard tool. And it's a great tool to use because it breaks down the project step by step of what you need to do. So on your first page, we can call this project whatever we want, right? Electronics cooling, right? And we can specify what configuration we want to link this to. So if we proceed next, the next thing that we have to do is just specify what unit system we're working in. Within that, if I don't want my temperature in terms of Kelvin, it's just a simple click of the pull down and switch it back to a Celsius, right? We can then proceed next, and this is where, probably one of the most important pages of this wizard is to specify, tell the software whether we're running an internal or external study. In this case, we care about what's going on inside this enclosure, right? So we're going to run with an internal study. We also care about the heat conduction that's going on within these solids. So I'm just going to simply flip that switch. And I also care about, I'm also going to turn on gravity, and this is going to specify that we have kind of this natural convection going on within these components as well, right? And it's just simple as that, right? If you had a radiation problem or you wanted to account for radiation, all it is just these simple check marks that SOLIDWORKS Flow Simulation will then run your analysis based on your boundary conditions and account for these automatically. If you go next, then the next page is what fluid are you using? You see that we have gases, right? This includes your basic air, any type of gas that you may be running, right? This is pre-programmed within Flow Simulation out of the box. We also can account for actual liquids, right? We can account for water, any type of, everything that you see here out of the box. We also can account for non-Newtonian liquids, compressible liquids there, real gases. We have hundreds, thousands of materials within this database, and of course you have the opportunity to customize them if you have something a little bit more unique. In this case, we're going to have air coming out of this, right, or going through this here. So let me just select air, hit add, and then proceed next, right? And then since, we obviously have bodies going on with this, we can give it a predefined body, right, material, I should say. So we can switch this to aluminum 6061, right? This is going to apply that material to all the bodies, but in the next few steps here, we're going to see how we can override that and apply a unique body there. Right? We also can account for the wall conditions here. So since we're doing an internal flow, we may want to specify a heat transfer coefficient value for the heat escaping that external box, right? So we can say that is seeing 8 watts per meter squared Kelvin, and then we can say that the temperature of the surrounding fluid is just normal temperature here, 20 degrees C. And then this is more for your external study, kind of telling what the external parameters are going to be if you have some kind of velocity going through the body. But again, we're only accounting for the internal analysis there, so we can skip this step here. And then the last page here, this is where the quality of our mesh is presented to us. And it gives it to us in this red-green bar, right? And what the red section is supposed to be, supposed to tell you is, this kind of quick and dirty type of result here. You just want to do a first pass to make sure that everything's flowing and working the way you're expecting it to, right? You don't want to have a refine at your first run through be at level 6, 7, 8, and then come to find out you set up the problem incorrectly, right? So you want to do your first couple passes maybe in the red zone there, but then when you want to go into final results, you may want to bump that up, up to 6, 7, 8 being the more refined, but of course that comes at a cost in terms of runtime. So in this case, engineers, they want the results quick, but obviously correct. So you probably want to be in the 5 to 7 range there. And that's it. We just specified this was step 1 as far as creating that project. We gave it all the internal conditions that we want. now we have to specify the boundary conditions, right? So instead of me setting up this problem from scratch, I actually do have a scenario here where I want to run internal fans within this enclosure here. And I already have it pre-set up here, and I'll just run through the general boundary conditions that we have here. So let it just load it up here. So now that I have that configuration up here, let me see. We see that we have, again, we want to run 3 different scenarios three different projects within this one study, right? And these 3 different scenarios are going to be fans running internally here, where if you take a look at that model, this is what we have. We're going to specify the fan going, an internal fan where flow is going in and then being sucked out from the other side. And we can also run a condition where we have an external fan where the fans are actually operating outside of the enclosure, right? And then we can have a scenario where our heat sink is more of a pin-fin type of heat sink there. And that's the great thing about this tool, right? We're able to run these different scenarios quickly without having to, save it out and again send it over to another analysis tool here. So the first thing that we have after you set up that wizard is you'll see your computational domain. And all it is just that whatever's inside that box, that's what it's going to account for, right? So generally what you do when you set up this problem is you go through step by step in terms of what you need or what you may not need, right? So the next thing that we have here is our solid materials, right? So if you recall, we specified that everything that we have in this model is 6061 aluminum. But of course, that's not the case, right? That's just the default material that we need to apply initially. We can always go back and add a solid material here. And all we need to do is physically select the components in our graphics area, and we can go into our predefined materials there. Right. We can also create one off this menu as well, where we can create a custom material, and it takes us again into our engineering database. Right. And this is what we did here in this scenario. Right. We specified aluminum for the heat sinks there. We then did this polymer material for the external case of the enclosure of the electronics enclosure. And then for all these components that are highlighting in blue, we specify these materials here. And the next thing on the list here is what we have is pretty much telling the software what the environmental pressures are in these conditions, right? So what we want to say is, if you recall in the original model where it has all those vents, that's where it's going to feel or see the air, right? So that's where there's going to be, that's where you would want to define your pressure differences there. So within that, we have a pressure one, which is going into those inlets, right? And these circular faces here represent those areas where it was meshed, right? Where it had that circular pattern where we have those vents. So we then specify what those that atmospheric pressure is, that environmental pressure at these standard temperature and pressure parameters here, right? And we did the same thing for our vents up top, where it's just seeing the atmospheric pressure, nothing really special about that, right? The next thing that we have to do here is, again, we're running the scenario where we have a fan, an internal fan going along these bodies here. And notice that the bodies are very general, right? It's just the overall shape of where we want to specify where that fan is. You don't have to have a complicated model, because we're addressing these fans, again, with a fan curve. So if I open up one of these fans here, it takes us into the fan property manager, and you see that we have all these different fans, all these different vendors. So there's a specific fan that you're using, SOLIDWORKS Flow Simulation will have it, right? But all of this really is, if I go into my create and edit, it's digging into our database here, and if I just randomly choose one of these, we can specify the properties of this fan. And not only that, what we can specify is a fan curve, right? And this is normally what you would get, if you've ever worked with this, is you'll have this kind of curve where you can input this now within our engineering database. If you have something, again, a little bit more custom, we can then reference that, and we can address those volume flow rates with this curve here, right? So what we did was we applied those fans to all those 3 areas here, which is the same fan curve that we're using. So we told the software now how flow is kind of going into the enclosure here. But again, this is not only is an internal study, but it's also a heat transfer problem, right? We want to see how things heat up, right? Our goal here is to model this, design this in a way where there's enough vents, where there's enough airflow, where things are going to be cooled down at a certain temperature that's based on your design constraints, right? And specifying those heat sources are really easy, right? And we have that section here for heat sources. All you do is just insert, some kind of volume source, or if there's just a specific surface that has a temperature, you see that we can input a specific power or temperature here. So if I open up the power, all we did was select those 4 components, and we said, hey, this is going to generate a heat power of 2 watts, right? We can do this in terms of the volumetric heat generation rate, or actually specify the temperature. And that's what we did here in this next component, where these components below the circuit board here, we said it's always going to see a temperature of 60 degrees, right? So these are the different ways that we can apply the heat transfer problem, right? The heat sources, the heat that's going to be generated within this enclosure. All right. So how do we now address the vents and the vents that we have here and the slits that we had at the top, right? How are we going to actually tell the software that we have air coming out of this body? Well, we can virtually do that within this perforated plate option here, right? And this is stemming from our engineering database again. So if I take a look at those circular holes, again, the body was there, the lids that we created there, that's what's representing the perforation there, the vent. So if I edit the definition for that now, we see that if I go into the database, we're just specifying, what kind of shape are we doing for the vents? It's a round hole shape. How big is that diameter? And then we can say how it's going to be covered within these lids, right? So again, it's quite a major assumption that we're making there, but it's to simplify the model, right? And it will recognize, it will understand that there is this circular pattern vent, and similarly to that, we can specify those vertical vents that we have, or those slots, if you will, on the top, and the same concept applies, right? You see that it's pre-selecting those spaces there. We can go into the item properties, and we can say, all right, in this case, we have these rectangular shapes, right? And we can give it the height, the width, and it's going to account for the surface area of that face that we selected there. So it's a good way to virtually apply this, these slots and vents to tell the software how air is going to be escaping this enclosure here. Right. The next 2 items that I'm going to show you here, again, are part of our electronics cooling module. And again, all it is, it's not necessary to have this. Everything that I'm showing you, you're able to do with the basic flow simulation. But the 2 resistor and the printed circuit board icons here, these are now stemming from electronic cooling. And all it is just a way to get finer accuracy, right? More options to set up your problem, but doesn't mean that you won't be able to do certain problems with flow simulation. It's just more the level of accuracy that you're trying to get. So for example, what a 2 resistor component is if we take a look at this, edit the definition here, all it is just a way to model the thermal behavior of the small electronic components, whether it be the CPU or the chipsets there, and how they're, and give it those thermal behaviors, those thermal characteristics there. So if I take a look at the create edit here, all we're saying really is how the heat is going to be conducted when that, let's say that chip is going to be joined by the case or the board there. So again, it's a way to not have to just do a general conduction value on a basic solid. We're actually telling it what that value is when it's in junction with the case and the actual circuit board there. So again, it's just a way to be a little bit more diligent, more refined in terms of how heat is actually going to be transferring from body to other bodies, right? We can definitely get away with this with just specifying what that conduction value is for just a basic solid. But again, it's just more accuracy, a little bit more diligent as far as what's actually happening. End result is just to get a more fine detailed result there. Same goes with this printed circuit board. So we can specify some, material for our circuit board there, give it some kind of conduction value. But what we can do, again, with the printed circuit board is a function. This is now, again, within our electronic cooling, is, the problem with that is, when we specify the circuit board is we can give it a conduction value that's in plane or through the through thickness, right? And that's what we specified here. When you do it just within flow simulation, you'll just have a solid body where you specify that value. But with this electronic cooling aspect here, we can specify the direction in which conduction is happening, and then we can even specify what those layers of that circuit board are, right? We can say, in this case, we have 4 layers within that circuit board, and we can tell it how thick that is, and again, just being a little bit more diligent about it, being a little bit more refined in how we set up our problem, end result is just to get a more accurate answer. But again, these are just additional things that are offered within flow simulation, but definitely able to do within the basic flow, just being aware of the assumptions that you're making. And that's it. That's our general setup, right? We told the software that it's an internal study. We told the software what materials we want to use, what the environmental pressures are when the air is being released, where our fans are going to be and what that fan curve is, and then we also have our heat sources. How is heat being generated? And then since our model had those perforated plates or the vent and the slot, we can account for that virtually within what's available in our database. And then, of course, our 2 resistor component kind of giving it the thermal information of how things are going to be joined within the circuit board in the case, and being able to specify, the different layers that are actually involved within the circuit board. The last thing that we have here is the goals. And it's not necessary to specify goals when you run this, but highly recommended. Because what this is telling the software is these are the parameters that we really care about. And once it figures out that result or that answer for these goals that we care about, the analysis tool is going to stop, right? It's not just going to find some kind of point of equilibrium. It's just going to say, this is what you care about? Okay, this is what I'm going to account for and try to converge to find you an answer. And some of the things that we may care about, right, is the heat going in, the fluid temperature that's going on within that enclosure, right? We may want to know what the volume flow rate as far as the air being circulated within that enclosure with the fan, right? And we care about all these different temperatures at all these different components, what that max temperature is, right? And all it is saying is, I want to know the temperature fluid, and I want to know the max temperature of that. So these are the goals that SOLIDWORKS is going to converge to. So the next thing that we do is just run the analysis. And I'm not going to actually run it. I'm going to show you the results already completed here, just because it does take a few minutes here to actually run. So let me load those results here. And what we have is we have a lot of different ways to interrogate the model, right? And to put it basically, again, we can start from the top and then kind of work our way down the list here. But what a cut plot will do is just take a slice within that model, and it will show us all the, depending whether you want to output temperature, pressure, velocity, it will output that information on more of a slice level. So if I show this result here, we have this cut plot, and you see that we're outputting the temperature of what's going on here. And let me get the geometry out of the way. So we can turn off the geometry, and we're just taking a look at that single slice, right, that we specified. And we see that we have high temperatures going on in the heat sink and where all those heats are being generated, right, that we specify in the heat sources. But not only are we seeing where the heat sources are, we're actually seeing kind of the flow that's going in within that body, right? What are the cooler regions of this body? What are very hot regions? And you see the flow kind of going through these different components here, right? Within the same plot, we can graphically change what we want to output, whether it be like the velocity of air going into the enclosure, right? And you see that we get that kind of effect. We get that effect where the fluid is coming out, kind of circulating within the body, and then now reaching like a colder endpoint here. Let me change this back to temperature. We can also change what our max is if we want. All I'm doing is just clicking onto the interface, and we can definitely change what our min and max values are, you know, in the range that we really care about. We can view it at a different angle here. So let me show my plot. You know, now we're looking at, you know, the cross-sectional here, right? So if you turn on your bodies, we're taking a look at that slice in that specific area. Now, let me show my other plot here just to kind of give you guys an idea of what's going on, right? And this, we can see, you know, the direction in which flow is going based on our vectors there. But the cool thing about this as well is, if I go back to my original plot, I can animate this, right? What if I want to look at a different plot here? Well, I can physically drag and drop and dynamically see the change in terms of how that temperature looks, right? And it'll just recalculate the results, or we can play our animation here, and this is what it does automatically on its own. It literally just goes through the embody and cuts through from top to bottom, right? And we kind of get an idea at the different levels in which this enclosure is getting hot. Right, at this point, you can use this and be like, is it reaching a maximum temperature where, you know, it's not fulfilling my design constraints? Right. And then lastly, again, since we're using an internal flow here, kind of seeing what the flow is going in through the body, we can turn on our flow trajectories here, right? Show that flow, the direction in which those trajectories are going. So if I zoom in a bit, kind of see the vectors kind of going in and kind of doing this roll effect. But what's really great about this is we can actually animate this as well, and we can physically see how flow is going into the body, right? And how things are going to be circulating around. So definitely a lot of great ways to interrogate the model, right? We can go back to our plots. We can choose a surface plot as well, right? If I want to know what the heat was specifically for that heat sink, and see, you know, okay, this is the range in which we're looking at for our heat sink, right? And this is a way to assist us in our design. So at this point, you as a designer, you may want to run a different scenario, right? The scenario being maybe a different heat sink pattern where we have a fin design here. So all we did here was just clone the project where we only specify the boundary condition once, and you know, and have it reference a different configuration. So just to kind of let you know or show you the different configurations here, you know, again, this is with the external fan, and then what we have is we have this. Let me show you my PowerPoint here. We have this type of effect where we get these different results where, again, we can adjust the model where we ran this initial case of internal fan, and then we did one where the external fan was set to this model, and then with the pin heat sink here. So with this, as you, the designer, we can take a look at and see, all right, what scenario is meeting our design constraints, right? Which one of these scenarios generates or is able to let the heat escape from this enclosure here, right? And all it is, again, because it's fully integrated within SOLIDWORKS, is changing the design configuration here, right? Changing these different aspects of the model, referencing that, rerunning the flow analysis with that new configuration. All right. Without that, if you weren't using flow simulation, you would have your model, have to save it again to a generic file format, send it over to the analysis tool, and then you know, have to wait longer turnaround time. Again, it's all integrated within SOLIDWORKS. Just a couple more scenarios here that I want to show you. So we also have here, we can do this exhaust flow design. And we want to run an analysis where the fluid flow is going into those internal passages, right? And what we have in blue here is, you know, the air going into this exhaust. And what we have represented here in this gray exhaust pipe is, you know, the flow that the dirty flow, right? The fluid that is, you know, kind of just the end result of this flow passage. So what we want to do is be able to design for, you know, if we were to put like a filter onto this space where you see my cursor, you know, we want as much clean air to go through that passage as possible. So we're able to kind of do this mixing type of scenario within flow. So let me open that up here. So we have this model again, And what we want to do is run through these different scenarios where the exhaust pipe might be just ending at that point here. So again, running through the different types, we can input what that air fluid is. So we want clean air going into this body, and we're referencing that phase. So if I edit the definition, we're saying that air is going through this body here, and we can specify this substance concentration. So we can specify this mass fraction type of scenario where in this specific phase going through this body, it's going to see 100% of that air, right? But you can see we can input different percentages in terms of how we want to mix these two fluids together within this example. In this case, I want clean air running through here. Again, I want as much of clean air going through this to hit our filter. And then we can specify a different fluid, right? And this is what I created custom here, and we're saying that now within this component, within this internal cavity, we're seeing 100% of this exhaust type of fluid here. So all I did was just use that default material. I created my own custom fluid that's going to be kind of showing this exhaust flow running through this, and our goal is to see how much air is actually running, or how much we want as much air going into that filter there. So if I take a look at my results now, you know, with this scenario where that exhaust pipe just ends at this point here, we can take a look at, you know, how that flow or that mass fraction is looking at in terms of this end phase here. And you see that only a little bit, or only about halfway hitting that filter here, right? So all this was is just, you know, we can go into our plot properties and say, I want to take a look at the mass fraction of the exhaust gas. And our goal, again, is to have as much clean air going into this body, right? So we can then run a different scenario where we may have an extended pipe here. So if I change that configuration, you see that the model changed a bit where we extended that pipe, right? So and then if I run take a look at the results again, let me load that up here. You see that we're getting, if I change now my plot to a mass fraction here, you see that we're getting a little bit closer, right? We can run this and see that we're covering more surface area within this, getting a little bit closer to this scenario. Well, we can then run a different design here where we may have a churn exhaust, and you see that the model now is, you know, obviously the exhaust is going in the direction of that filter, right? So again, we can take a look at those results, and then we'll have something that looks like this, where, you know, now we have less surface area that is seeing that clean air. So again, what I want you guys to kind of, you know, realize and kind of, you know, see and take a look is we're able to change these parameters of the geometry very fast. Of course, it took some time to actually model this and have these different cases, but we can always go back and reference and see how these plots change, how these results change based on the model, right? So, and then, you know, we can go into our results here, and, you know, and based on the different plots, you know, whether the initial concept where the end of the exhaust is met at that coupling there, or it was actually extended or curved, you know, we may want to run with the extended pipe just because a lot of that clean air is actually touching that filter, right? We don't want that dirty air, that exhaust fluid to be going into that general area. But again, we're able to utilize this mixing scenario within Flow Simulation here. The last scenario here that I wanted to show you is doing more of that what-if condition. So in this case, I have this LED lighting assembly here, and I want to run, again, a thermal analysis. And I want to see how heat is going to be dissipated within that body with different fins that I may have here. So if I open up this model, we have this lamp. And if you look closely, we have this kind of red, pink color type of component here, and that's representing the fins going on within this assembly. So let me open that up here in a sec after it finishes loading here. And I just want to show you what that model looks like initially. So what we have is, if I open this up, we created this model where it has 20 pins here. So in this scenario, what we want to do is have Flow Simulation assist us in terms of how heat is being released or how hot these LEDs get as I add more pins to this body, right? So what we have is this parametric what-if study that we can run through. So if we go into our solve parameters, we can specify a parametric study. Actually, I already have one created, and it's very easy to use, right? So the input that we want is that circular pattern that we created for those pins. And you see that we can specify how we want to change this. I want to run a scenario, this what-if condition, when I have 20 pins, 40, 60, 80, and 100 pins. So I'll run through, change the model, and give you, and then what you care about is the temperature at, in this case, these 4 LEDs here, since it's the more central part of the lamp. So I want to know how hot these areas get as I change my pin count, right? And the goal is to really see how much heat is being released from this body, how hot things get as I increase or decrease the pin count. And after you run your analysis, you'll get something like this, where you have the temperature at all those 4 LEDs that we want to, that we were interested in seeing as far as the parameters, and then the different variables, right? At 20 pins, 40 pins, 60, 80, and 100. We can export this data into Excel, where we can then graphically see how this change is affected. So if I go back to my PowerPoint here, you see that we now have the different counts here, right? Pin count versus the temperature. And you may, you may have the assumption where as I increase the pins, the more heat is going to be dissipated, so therefore a lower temperature value. But in this case, Flow Simulation actually helped us out, right? Helped us clear up that assumption for this specific model that, in this case, the 40 count scenario was the one that had the lowest temperature. So in this case, we may want to run with that design choice in terms of it will dissipate the most heat. It will see at those LED locations a temperature of about, close to 90 degrees there, and it's the lowest value at that 40 pin count there. So these are the different ways we can definitely utilize that what-if condition, and kind of vary our model, see what we're interested in, and then give us this data here in a table format in which we can export. Okay. So, and these are all the scenarios that I wanted to run through here. So hopefully this gives you a good idea in terms of what we can get out of and what we can do with Flow Simulation, right? Again, we can run through a thermal fluid condition there. We can run through internal, external fluids, and this is, again, just the tip of the iceberg on what we can do with the CFD tool. So hopefully you guys, again, enjoyed that little presentation in terms of the different ways we can use that CFD Flow Simulation tool. I also want to let you guys know that, of course, with any product that that we sell, we have a training that's linked to it, right? Whether it be an in-person or online. So what you see on your screen here is the upcoming classes that are coming up for Flow Simulation in the different areas, right? So we always have this class running once or twice monthly in all the different areas here, and you can see all the topics that are covered within the training class there. As far as getting trained on the additional add-ons that we have, like electronic cooling or HVAC, those are offered online. So we do have online courses here, and these are the different ones that we have where we can run through in this industrial flow type of scenario, electronic cooling, and using this rotating machinery type of condition here, where, again, you can take a look at our Hawkbridge page, www.hawkbridgesys.com. Take a look at our training schedule, and it'll give you all the information there that's needed as far as when and where these trainings will be held. I also want to let you guys know that we do have simulation services here at Hawkbridge Systems, right? So in addition to our classroom training, it's more of an extension of what we get out of what we learn in our classroom training there. So, of course, within that training that we get within our, from the regular flow, from the regular training, we can do a training class a little bit more specific to your project, right? Something that, you know, is more specific to what you're working with. You know, what you'll see within a general training is you'll get into different topics just to show you how the interface works. But with simulation services, we can fine-tune that specific, tailor it to what you're working on there. We also have the analysis consulting aspect of it, where if you have a big project, if, you know, time is an issue and you need, you know, something kind of done correctly and done in an efficient manner, you know, we do have this consulting services where, again, we'll work with you, sit one-on-one with you, and kind of state, you know, what are you trying to get out of the software, and, you know, and run this project for you. The simulation services team is also giving you the simulation credit, where if you do utilize our simulation services and decide, hey, you know, this software is actually pretty great, I want to use it on my own, you can use 25% of that, the simulation services fee, and apply it to a purchase of a SOLIDWORKS license there. So if you have any information or want any more information on that, you can contact Jared Conway. He's the simulation services manager. You can contact me as well, and I can forward all that information to the necessary people involved. So just want to let you guys know as well that the upcoming events, we do hold these webinar Wednesdays every Wednesday. We have an e-learning where it just goes through the different tips and tricks. They're held every Wednesday at 11 a.m. And these are just a couple of them that are coming up. So we have the CAMWorks e-learning and the SOLIDWORKS Composer. And then what I just did, which was an eDemo, just showing you the software in terms of the capability. We have something coming up for SOLIDWORKS Electrical and 3D printing. So definitely go ahead and check those out. You can sign up from our website here. And the last thing that I want to do is just give you guys a big thank you for attending. Thank you for taking time out of your day to kind of check this out. Again, if you have any questions, feel free to, you know, ask those questions in the panel, in your GoToWebinar panel there, or you can contact me directly, or if you have any support questions, you can email the support line there, or again, everything that you need is within our hawkersys.com website. For any other webinars that you may have missed, we do record these on a weekly basis, so there's the URL link in terms of where you can find it. There's my email if you have any questions, and again, thank you for attending. Hopefully you guys enjoyed it. Have a good day everyone.